Good evening, everyone. I'm Calvin Joseph, and today I'll be conducting your week 3 problem solving and doubt clearing session for this course, Digital Electronic Circuits. So, we'll be studying various things such as 5 variable K maps, various hazards which are the optimization of logic gates. Okay, so those things we'll be considering. Further, we'll also be solving sums, and it will be useful for you while you will be solving the assignment sums. Okay, also I'll be showing certain simulations so that you can get a more good understanding about the various hazards which sir has described in this course, in the lecture videos. Okay, so I'll share my screen. Okay. So I'd like you all to be interactive, to ask questions, doubts, and everything. So today is the week 3 for digital electronic circuits. Okay. So the first topic which sir covered was the 5 variable K map, Cornell map. So earlier I told that only 4 variable would be come, but then in this week, sir has also included 5 variable K map. So how do we go about solving that? Also, we will be looking into. Then another thing which sir taught was the extended variable map. Then sir taught about optimization of logic gates. Then sir taught of hazard, static type 1 hazard, static type 1 hazard. Then there is static type 0 hazard. Also, sir told about dynamic hazard. Okay, so we will start with the 5 variable K map, and we will look into how do we tackle this sum. Okay. So we will learn about the 5 variable K map directly by solving a sum. Okay, so let me start the sum. Okay. So this is the question. These are the options. Okay, so there are 5 variables. Okay, A, B, C, D, E. So we will start with the way by A, B / C, D, E. Okay. Then AB we considered how 0, 0, 0, 1, 1, 1, 1, 0. So this is very important to go in this order. Okay, you should not miss this order. Then what we used to do, we used to have a 0, 0, 0, 1, 1, 1, 1, 0. This is in the case of 2 variables. But now you add a third variable. So what you do? You add a 0 here, a 0 here, a 0 here, and a 0 here. Okay. So this is got half your blocks. So this now we need to add the next half. So how you add the next half is you draw this line known as the reflection line. Okay, there's a line known as the reflection line, and then this is 0, 1, 0. you follow the same thing. You again put your 0, 0. No, you don't put your 0, 0. You go in the reflection. That is, this is some from, if you go from the right to left, that same part you will go from left to right. So you will add the same thing. 1, 0 you will add. You'll have 1, 1 you will have. Then you'll have 0, 1 you will have. And you'll have 0, 0 over here. And you will add your 1 over here. 1 you will add 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 here. So this is the way you will construct your 5 variable K map. Okay. So what I'd like to again reorient you, retell you is you have your 0, 0, 0, 1, 1, 1, 1, 0. This is from, let us say this is from right to left. Here you start from left to right. You use the 1, 0, 1, 0 here, 1, 1, 1, 1 here, 0, 1, 0, 1 here, 0, 0, 0, 0 here. And here you put in 0 here, that is your C0. Here you put your 1 over here. Okay, so this is the way you draw the 5 variable K map. Now, let us complete this. So draw like this, the lines, make the separation. This is done. Draw these rows. Okay, done. Now, it is important to number it. So I was like practicing and I was finding it difficult to remember how do you properly orient. So what I thought is, even though it may take a little more time, it will help to reduce the probability of making a mistake. So let us number this. So we will start. So this will be what? 0. This is 1. Then this will be 2. This will be 3. Then usually we start 4 here, but 4 will not start here. 4 will start from here. 4 we start here. 4, 5, 6, 7. Done. Now we start here 8, 9, 10, 11. Then we have to go all the way here. 12, 13, 14, 15. Then we have to go here. 16, 17, 18, 19. Then here 20, 21, 22, 23. Okay, then we go back here 24, 25, 26, 27, 28, 29, 30, 31. Okay, so this, I'll advise, this is a way you can, know it thoroughly. How do you actually construct your K map? So it becomes easier, it reduces the chance of you making an error. Okay, so this is done. Now let us add the variables. Okay, let us add the variables. So we have 0. So you add 0 over here. 2 you have. So you add 2 over here. 10 you have. So 0, 2. Then 8. 8 you add 1 here. 10 you add. Then you add 11. Where's 11? 11 is here. Then 13. 13 is here. 16 is here. 18 is here. 24 is here. 26 is here. 29 is over here. Okay, so we have added whatever is the main variables. This D, we have added the min terms. Now the D stands for don't care. So for don't care, we will put 5. 5 is there. Then you have 6 is there. Then you have 9 is there. You have 14. 14 is here. You have 21. 21 is here. 22 is there. And 30 is there. Okay. So all these things are added. Now we have what we have done is we have first constructed a 5 variable K map. We have added where the min terms are. We have added the don't care. Now we have to group them. So we have to group them. So now we will group relative to this. Relative to this axis, we will group. So how do you combine? You combine it like this. This is one combination which you can combine. That is, one is the simple combination. You combine this like this over here, like this. Okay. So what would be this output. Okay, so let us write y, this output y for this green combination. What it would be? It is C d bar E. So it is C d bar E. Okay, so that is one combination. Now we will take this combination. We can either have this one, or we could have just done like this as well. It's up to us. Both combinations work. Both combinations will give you the same correct output. Okay. Then so this would be, this is what, if you see in this case, D and E are fixed, D and E are fixed. Only C gets changed. So this actually is your DE. DE. Okay, this is your DE. Or what it could be is, since it is this 111 only is important, you don't care about them. If you want to work in that method, then this would be your C bar D. Okay, sorry, this is DE bar, DE prime, DE bar, DE bar, and this is C bar DE bar. Okay, so this is for the gray part. Now we have this also, material color orange. Okay, so we have this part over here like this. So this is given by C bar D bar E bar, right? C bar D bar E bar. Okay. And then we can also have this combination. This color, this combination. Okay, so this would be your, it is A bar B, and over here what is remaining fixed is the variable C. So this is C bar. Okay. Any doubts in this part? No issues? Okay, so because this is a 5 variable K-map, this is not what you usually do. I will go through it again. So this is the 5 variable K-map which we have to solve. A bar, B bar, C bar. Okay. Green, right? Okay. So for the green one is, let me, so you're talking about this one, right? This entire one. So if you see in this row, this is A bar and this is B. This A bar and this is B. And let me write it. It makes more sense. So this is actually your A bar, B bar. This is A bar, B. This is A, B, and this is A, B bar. This is what your C bar, D bar, E bar, C bar, D, E, C bar, D, E. This is C bar, D bar, E, and this is C bar, D, and E bar. So if you see in this part, this side, this portion is actually C bar. This actually portion is C bar, and over here, this portion is C. So that is why when we are drawing this green term, that involves A bar B is fixed in that case because it is in that row. And in all the columns, what is not changing is C bar. So that is why it is A bar B C bar. Okay. Hmm. Okay, so in this fashion, you can write it down. Hmm. All right. So we'll proceed. So this is for the five variable K-map. And now we will start a different thing, which is known as the extended variable map. Okay, extended variable map. So how do we solve this extended variable map? Okay, so let me say, first of all, there's one issue over here. Hmm, something that can be simplified. So uh, this one. So this one corresponds to this, right? And this one corresponds to this. Okay, so if you will write y, if you will write your y is what? C d bar e. I am not using this because it is don't care, so I'm just using plus c bar d e bar plus c bar d bar e bar plus a bar b c bar. Okay, now if you will see y, it is c into d bar e plus c bar and d plus d bar into e bar plus a bar b c bar. So what is d plus d bar? Can anyone tell what is d plus d bar?
It is 1.
Yes, very good. So d plus d bar is 1. Okay, that's why y, it is c d bar e plus c bar e plus a bar b c bar. Okay, so this is a kind of simplification, and actually the issue was I did not see the k-map properly. So when you have what is known as a four variable k-map, if you have a four variable k-map, then these sides also you must also watch out for this column and this column, that they are adjacent, they're actually adjacent to each other. So that's why you can group this like this and group this also like this. Okay, and that when you do, that is your this term. Okay, all right. So so this is regarding the five variable k-map. So you'll have to get comfortable with k-maps. And as I said, it is best to number. Numbering is very useful. Okay, numbering is very good. That way it removes confusion. Although it may take some amount of time, it would be good to number it. So what would happen is usually you would have solved this sum, and when the exam comes, you will not know why you put the one here, why you put one there, why you put zero here, why you put zero there. It doesn't make sense. Similarly, this concept of this is a b bar, this is a bar b bar. All these things you can add. You can add it when you're solving the sum so that you will remember it when you refer to it. Because you will do it now, then you may forget. Then later on, when you do, you'll have to go through it all over again. But if you add these extra things, which are little bit not necessary all the time, but can help you to grasp it, understand it well, then it will make your life simple. Hmm. Okay, great. Then, mm, page. Okay, we'll consider the extended variable map. Okay. So sir has used one example. So we'll refer to that example while solving. Let us say we have A, B, C, Y. Okay. It is 0, 0, 0, the whole truth table 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Okay. 1 0 1 1 1 0 1 1 1. Okay, so this is the overall table, and we give some values. So let us say, okay, can you tell us some values? What should I write here? 1 or 0? What value should I give here? Hello? Are you guys able to hear, or is the external sound disturbing? Hello? Okay, so let us say ABC, when all are 0, we use value 1. Then we can use the value 0. Then we can use the value 0, 1. We could use all 1, 1. We could use all values 0, 0. So now we have to write the truth table in terms of C. Let us say we have to write the truth table in terms of C. So let us say this is your A and B, and this is your Y. So if A and B are both 0, A and B are both 0, that is, it is what case? It is this case, this case, this case, this case. So what is your output Y? Your output Y
C bar.
is C bar. Correct. It is C bar. Suppose A and B is 0, 1. So what is your output Y in that case? There is
C.
0, 0, 1. It is C. Good. If it is 1, 0, your output would that case be, it would be 1, because Y is always 1. And if it is 1, 1, your output in that case would be 0. Okay?
0.
All the time 0. Okay, so this is how we are writing the truth table in terms of another variable, in terms of another kind of input variable. So that is what is known as the extended variable map. Okay. Now let us try to draw the K map of this. So what is the K map of this? So, okay, let us do it all side by side to make more sense of it. So this is your A, this is your BC. Okay, let us draw the actual three table K map, three variable K map, and let us see. So this is your A bar, this is your A, this is your 0, 1, this is your 0, 0, 0, 1, 1, 0, sorry, 1, 1, 1, 0. Okay, so again we do 0, 1, 2, 3, 4, 5, 6, 7. So let us enter the values which we have got. So 1, 0. So it is 1, 0, 0, 1. Then 1, 1, 0, 0. Okay. So what would be the K map of this? What would be the output Y in terms, in min terms? What is the output Y of this? What is this output Y? So
B
output,
bar, C bar.
okay, B bar, C bar. Okay, good. Plus
A bar, B, C.
A bar, B, C, good.
A, B bar, C.
A, B bar. No, A, B bar. A, B bar is fine, right? This one. So it will be A, B bar, right?
Yeah, then A, B bar.
Yes, yes, A, B bar. So we have three. So you have done this one, then this one, and then this one. Okay, three are there. Okay, so let us try to get the same output using the simplified way. Okay, the other way, extended variable map. So in that case, you have your, this is your map, this is your A, this is your B. This 0, 0, sorry, 0, 1, 0, 1. When A is 0 and B is 0, it is C bar. Okay. When A is 0 and B is 1, it is your C. When A is 1 and B is 0, that is your 1. And when A is 1 and B is 1, it is 0. Okay. So now how do you find the K-map for this? How will you get this value? So one is we consider for this term. Okay, let us consider this term. So this y, what is this y? This happens when a is 0, b is 1. That's why it is a 0, a bar, b is 1, b, and c. So it is a bar, b, c. Okay, well and good. Very nice. Now we have for this term, let us say this term. What is this term? It is a is 1 and b is 0, so a and b bar. Okay. Next term which we will get is we have to do for c bar. Okay. So what you can write is this 1. This 1, the 1 which is over here, this 1, you can write it as c plus c bar. Suppose you write it as c plus c bar. Okay. And then you will group it. Then what you can do is you can group this thing. When you group it, you will get B. It is what B bar and C bar plus C bar. Okay. So then what is your Y in that case? So Y, these first two terms remain the same. So that is what A bar, B, C plus A and B bar plus B bar. And what is C bar plus C bar? What would be? What would be C bar plus C bar? What is that value?
C bar itself.
Yeah, it will be C bar itself, right? So you have C bar or C. So what would you get from that?
It's 1.
It is 1. Okay, there is some mistake I have made. It is not the correct output. What is the issue with that? There's a mistake. Because what I remember, what I recall is, what you will do is you will club this 2, okay, and you would, because it is B bar is common, and you will also take C bar, if I'm not wrong, common. So it will come out to be B bar dot C bar. How exactly? I just check it once more. Mhm. The reason behind that. Mm. Okay. So what you look into is if it is a C bar and if it is 1. So you can write that 1 in terms of C bar and C, and you can combine that. And when you combine that, you have to write it in terms of that variable which is there, that is C bar. So then that is why I'm getting it in terms of B bar and C bar. Okay, so this part was wrong. This part is wrong. So it is just you have to write it as B bar and C bar. Okay. Hmm. Okay. So shall I proceed or you want to me to further discuss about this?
You can go with it.
Okay. Okay. So this is with the extended variable map. Now you have till now what you have done is you have just considered logic gates and you have used Boolean expressions. Okay, you've used Boolean expressions. and you have no propagation delay you have considered. You have not considered any propagation delay. Okay, you have not considered any propagation delay. What you have used is you have used K maps, and as you have used K maps, what you are trying to get, you are trying to get a logical expression. Logical expression that uses your logic gates to get your desired output. Okay. So in K maps, what do? Is we try to minimize the number of gates. That is the objective. Okay. Till now, what we are doing, we have A, B, C, and we have an output Y. But what if you, instead of just having Y, you have Y1, Y2, Y3, etc. You have an output Y1, you have an output Y2, you have an output Y3. Then how do you deal with such a issue? That is, you have to do what is known as optimization. Okay, you are essentially, what you're trying to do is you are want to do optimization. You want to say that I want to do, like, I want, let us say you want to study digital electronics, you want to study analog electronics, you want to study this, that, everything. You want to study multiple things. Okay, you want to study control systems. Okay, you want to study VLSI, many things you want to study at a time. Then if you want to optimize your output, your result, what you should try to do is you should try to focus on those aspects which are common in all subjects. If there is something which is common in all subjects and you master it very well, okay, you master it very well, you're very good at it, then it will help you in wherever it is required. So you try to find something common. Okay, you have to try to find something common. Okay, so if you are able to do that common thing, then when you study the next subject, you don't need to study that part all over again. Okay, that's some kind of way. It's not a very good example, but a kind of crude example of optimization. Optimization in terms of logic gates is you try to find those blocks which are common in both outputs, in Y1, Y2, Y3, which output is common in both cases, so that we can use that. Okay, we don't need to again generate that output. Okay, so that is optimization. Okay, then there are certain ways we calculate the cost, or that we can just go by an example to make it more easy to understand. Okay, yes. So let us consider this example. Okay, a very simple example. Question one, question two. Also, I will share some important links. Okay. So I have added the links. This is the link where you can get access to the YouTube channel where this videos will be uploaded. For the Drive link, which has the access to the notes, where the notes are being uploaded. Okay, and Mitesh, you have asked a question that what is exact meaning of don't care and why consider in KMAP? Okay, let us do a simple example for that. Okay, let us say you have we'll do very simple. We'll have A and we have B. Okay, this is your 0, 1, 2, 3. Okay, your 0, 1, 0, 1. Now your output could be 1 here, everywhere else it is 0. And here we don't care about this output occurring, that we don't care about this output occurring. This would be in which case, why would this happen? Let us say, so you have A, B, and you have Y. Okay, you have 0, 0, 0, 1, 1, 0, 1, 1, right? Output in this case is 0, 0, it is 0, 1, 0, and X. That is, you don't consider this happening at all. So what that means is there could be one case where A and B both are equal to 1 is not occurring. Okay, this is not occurring. It will not even happen. Like an example of a SR latch, SR flip flop or something, where S and R both cannot be one at the same time. Then you don't have a properly defined output. Okay, you don't know what is exact output. That was one case. Similarly, another case could be that in Sir had talked about what is known as a BCD. It is a binary to decimal converter. So BCD will have 4 bits. 4 bits means your range can go from 0 to another case where it is 4 bits where it goes from 0 to 15. Okay, but your decimal can only be from 0 to 9. Okay, so that is why when the inputs is between 10, 11, 12, 13, 14, 15, the output which is undefined, it is not defined output. There's an undefined output. So in such cases, we use this don't care, this X. And when we use this don't care, we can make our output simple. Okay, let us say for this case, okay, A and B, what you would say is your output Y. Your output Y in this case is A bar and B. Okay, it is A bar and B. But if you consider don't care, you can assume X is 1 and you can combine it. Then you can write Y is equal to B. Okay, so then this is much more simpler to implement. This doesn't need this, what you need a NOT, then you need an AND gate, all that you need. But when you consider the don't care effect, it's just simple, Y equal to B. Okay, so that is the advantage of using don't care. Okay, yeah, all right. Okay, so now let's get back to the question 2. Mm, Question 2. Okay, we want to realize this function. Okay, see, corner map, you have to know it very well because it is there, here and there, here and there many times. Okay, so you should learn how to do it very well. Okay, so we have what? F1. Okay, that is A and B, C. So this is what 0, 0, 0, 1, 1, 1, 1, 0, 0 and 1. So what is this? This is your 0, 1, 2, 3, 4, 5, 6, 7. Okay, 1 means what? So this is 1, 3 over here, 6 over here, and 7 over here. Okay, very good. Now let us see for F2. What is it for F2? Again, we will draw the corner map. This is A, B, C. Okay, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, we have in here, it is for 0, it is for 2, it is for 6, and it is for 7. Okay, I didn't write here because it's already written next to it, so I can easily know it. So now, if I want to implement this corner map, I want to get F1 and I also need to get F2. What you do is, you combine. You will draw, this is one combination, this is another combination, this is one combination, and this is another combination. Because they are logically adjacent. This one which I did in dotted, why I can do that? It doesn't seem to be next to each other, but they are logically adjacent. And why they are logically adjacent is because over here it is what? B and C bar. Over here it is B bar and C bar. Only one bit is changing. That is why they are adjacent. So that is the reason why we construct corner map in this case is you have 0 and 1, you have 0 0, then you have 0 and 0 1. So it is changing one bit at a time. So you must always remember your corner map should be constructed in a way it is changing one bit at a time. But we cannot do this rightmost and leftmost. We have to understand that there also it is changing one bit at a time. So that is why they also are close, like they also are adjacent to each other logically. Okay, so that you have to know and write down. Okay, so now if we will do what is your F1, so these are your min terms. So F1 is in this case for this one it is A bar because A bar is common, and over here which is common, C is 1. C is 1, that is common. So it is A bar and C. Next one over here it is A is common because it's in the row A, and what is same in both the columns, that is B is 1. It is A and B. Okay. Similarly for F2, what is it? For the first row, it is A bar. And what is common in B C bar and B bar C bar? C bar is common, so it is A bar and C bar. And then for the bottom, it is A. And what is common for 1 1 is B. So it is A and B. Okay, so if you will observe this gate, if you will draw it, what you will get is you have one AND gate like this, which has input of A bar and C, another AND gate like this, which has the input of A and B, another AND gate like this, which has the input of uh, A bar and C bar. Now you OR this two. This is your F1. You OR these two. This is your F2. Okay. So what is common to both is this part. This hardware or this logic gate is common to both. Okay, so that is one thing we have to keep in mind that helps us. That is helpful. That is why we are having two outputs and we are optimizing it based on the two outputs. Okay. So now we have to find out what is the cost. What is the cost of it? So you tell me how many inputs are there? What is the total number of inputs to the logic gates? And okay, let us first start simple. How many logic gates are there? How many number of logic gates are there?
6.
Why are there six logic gates?
Sorry, 5.
Okay, five logic gates. Good. And how many inputs are there to the logic gates? Total number of inputs.
6.
Hmm. What about others? Okay. So there are actually 10. See, this is an input, 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 this is an input. Then this is also an input. 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 So there are totally 10 inputs. Okay. So your total cost is the number of inputs plus the number of gates. So that is 10 plus 5. That is equal to 15. Hmm. Okay. All right. It will take some time. Till now we are very used like digital electronics, 0 1 1 0 1 1 all that. Only one output, only one output. You're thinking in terms of only one output. But when you will do your projects and when you go for your work, you have a complex system and there you have many outputs, many requirements. So that time you need to optimize like which one is most critical, which block can be used somewhere else as well. So all these aspects are there. So just to get you, this is just the start. This is just the start. This is the very basic stuff. Okay, so here you're just trying to get the idea of learning how to think as an engineer. Okay, engineer tries to optimize, tries to make sure that he gets the desired output, he should get it with a minimum number of things utilized. Okay, so that's why this is the optimization thing which was considered. Okay, so now we have seen this method. There is also a QM algorithm is also there. So we can look into this QM algorithm as well. It is a bit time consuming. So we will take it up at the end. We'll take it up after some time, not immediately, because it is a little bit complicated. So let us start with this. We'll start with something known as static one hazard. Is static one hazard. So now you have what is known as A plus A prime. What is this value? What should be this value? Should it be 0? Should it be 1? Should it be equal to A? A plus A prime is 1. Okay. So Basu has told correctly it is 1. Now, how do you implement this like this is a Boolean expression. You must understand that this is a Boolean expression. How do you implement it practically? So you have an OR gate is there, right? You have an OR gate here. You will have A over here. A is there. Then you will have a NOT gate over here. You will have a NOT gate, and you will get what you will get. You will get your A bar over here. Okay, you will get an A bar, and then this is your output Y. Okay. Now, see, many things work fine when everything is normal, but when some change happens, then you know what they say, the true colors show up. Okay, so this is something like that. Your A was 1. A was 1. What was your A bar? Your A bar was 0. Okay, your A bar was 0. Now from 1, A goes to 0. Your A bar also has to go from 0, it has to go to 1. But it takes some time because there's a delay. There's a delay here. Okay, there'll also be a delay over here. So instead of going to 0, instead of going to 1, it will still be 0. Then after some time, it will become 1. Okay. And here, and this will continue to be 0. This was initially 1. But since there's a condition where both are 0, 0, it will be 1. After delay, it will go to 0. And after the delay, it will go back to 1. Okay. Okay. Did you guys understand this? Okay. So to just make this very well understood, this is simulation which I had run. I'll just show that simulation. So static one hazard. Hmm. Will you open up static one hazard right here? So you're able to see the simulation screen, right? Okay, I'll trust you guys are able to see. Please be a little bit more vocal. Okay, so this is a simulation software known as Simetrix Simplest Elements. Okay, this is the free software. The Simetrix Simplest is a paid, expensive software. The They have a free, reduced, small scale version of that known as Elements. Okay, so I'm using this Elements version, which is free. So if you have time, if you're interested, you can also check this out. Okay, so what I have done is I have this OR gate which was there is same. This is your A signal, A input. This NAND, when both the inputs of the NAND you connect, it acts as a NOT gate. Okay, so this is implementing a NOT gate. Okay, so let us see how the output looks like. And this is like a square pulse. It goes high, low, high, low. So let us see how it looks like. So let us run it. Okay, this is how it looks like. Move myself out of the way. Mhm. Not reducing. Okay, let us say this is where the problem is. Okay, it is this is A. This input is A. It is going from 1, it is going to 0. From 1, it is going to 0. At that time, what happens? Your A bar doesn't go directly 0 to 1. It has a delay. That is the delay of your logic gate. And because of that delay, and your OR gate also has a delay. So they are further delayed so much. Okay. Let us say over here. Okay. I think this will be better now. So at this point, A fell. A went down. And A bar, it took more time. It took little more time. Like it has a delay and then it has gone high. And your OR gate, that is the output of the OR gate, it was initially 1, then it remains 1. Okay, because it has a delay. And the output which it should show that when 1 and 0 is when 0 and 0 is connected to the OR gate, what value it should show? It should show 0. But it doesn't show immediately because it has a delay. So because of the delay, after that delay period, it goes low, 0. Okay. And then it's like when it is over here, in this case, between 510 to 520, the output ideally should be 1 because it is input is 1 and another input is 0. So 1 or 0 is 1, but because of the delay, it takes time to respond, and after the delay, it becomes 1. Okay, it becomes 1. So this is the thing about static 1 hazard. It What it means is your output should be 1. It should be 1. Regardless of how your input will change, you want your output to be 1. But because of the delay in your logic gates, there is a condition where this can fail, where there is for a small duration, which is dependent on your propagation delay of your logic gates, your output will have a glitch. So that is why if you see the zoomed out version, that is, if you see from this point to this point, the output should have remained 1 all the time because the truth table says that 1 plus 0 will be 1. That is, A plus A bar is 1. That is like you have written like a some postulate from some famous guy's name, everything. But when you go to the practical circuit, when you're practically trying to implement it, there is a small region, which is because of the actual practical delays which are present in the circuit, there is a glitch. A glitch is happening. Okay, so that is known as a static 1 hazard. Okay, so this static 1 hazard. Any doubts in this? It's a new concept. I maybe new for you, maybe you know it. But if you have any queries, you can ask me. And since this is simulation, you can check it. We can also check what will happen with the delay. If the delay is less, if the delay is more, what can happen? Okay, so let me just add a simple point. Currently, the delay is 10 nanosecond. Let me make it 15 nanosecond, or not 50. Let me make it 25 nanosecond. Okay. For the OR gate also, let me make the delay to be 25 nanosecond. Okay. And now let us run it. So if you see, the blue waveform is my input. It doesn't change because my input I have not changed. But because of my delays being changed, you can see there's a shift. See this light green curve which you see? That was the previous simulation. Okay, and this current dark green curve which you see, this is the current simulation. So when I've increased the delay, the time when it has this glitch also changes, and the amount of duration of the glitch also changes. Okay, all right. So this is a bit of a different thing. Uh, just thought, like seeing it in the actual screen, actual simulation is very useful. I would highly recommend you guys when you get time to download the simplest elements, and you can actually run these. You can make the circuits in simulator and see for yourself. Seeing is believing. You can see the output. You will feel very nice when you see the outputs coming on the screen matching to what sir has told. You're able to see what you're learning happening and all. Okay, so this is one thing. I highly recommend you guys to do it. Okay. So now we have seen there's a static one hazard. And this has been shown for this case, but when you have a complicated system, that is you have A and B plus A bar C plus B and C, something like this. When you have this big complicated system also, you can have a hazard one. Hazard one can occur. It can occur. Okay, so to do it, to overcome this hazard, what they do is they add redundancy. They add redundancy. That is, certain logic gates you may not require. Like what we studied previously, we studied optimization. Redundancy is opposite to optimization. Optimization means what you want to have minimum, the bare minimum, the essential. You wanted to have the essential logic gates required for you to get the output. But when you go for actual practical systems, like if you have your spacecraft or very important systems, or like your aircraft, the aircraft will not have only one engine, it will have two engines. That is, even if one engine fails, your second engine can still cope up. Okay, in very critical, important equipment, you have one or two things there, so that in case one fails, the other thing can take over, the other thing can also function. So that is known as redundancy. So there's one perspective where you optimize, where you try to minimize, cut short, and only have the essential things. Another way is redundancy, that is, you add a slightly little extra such that you can be sure that you can eliminate this hazard or this fault. Okay, so that is one thing. Okay, so let us try to see it through examples, like solving these sums are very useful. Hmm. Okay, so sure. Okay, let us try this sum. Hmm. Okay, so this is the thing, we have to find the truth table. First, we have to draw the K map. Okay, let us draw the K map. You have like this. This is AB, this is CD, this 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Right? Then let us number it again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So we have numbered it. Now let us put what are the values. So 0 is there, 2 is there, 5 is there, 6 is there, 7 is there, 8 is there, 9 is there, 12 is there, 13 is there, and 15 is there. Okay. So now, how can we draw the K map? We can draw the K map like this. Okay. Like we can have a K map. This is one K map we got. Okay. This is another K map we got. Right. This is another K map we got. And this is another K map we got. Okay. So let us write what is the output Y. So for the first four circle K map, it is what? It is given by A and C bar. Okay, I should have used different colors to be better that way. Mm. With that, let us do one by one. Let us make it more sensible. So this is one came up, right? This is another came up. This is another came up, and this is another came up. So the output y is equal to, for the red one, it is what, a and c bar. Okay. For the blue one, what it is? It is b and d. For the orange one, what it is? It is a bar and a bar and c and d bar. Okay. And for the purple one, it is a bar and b bar and d bar. Okay. A bar and b bar and d bar. Now this circuit will give you your output. It is supposed to give you your output. But what you should do in addition to this is, you must add additional linkages, additional redundancy, which I was talking about. That how do you add it is, you add this. This also you add. And you add this also. You are linking it. It is not by, if you just go by the K-map method, this will give you your output. This is fine. But if you want to avoid that possibility of getting that those hazards, you link it. So what you do, you add plus, what is the first linkage? That is, what is this linkage? That is actually equal to, in that case, your B is B bar and C bar and D bar, plus for your next linkage, it is actually A bar and B and C. Okay. If you do this, then you can be assured that you don't have any hazard. Okay. You're overcoming the hazards. Okay. All right. So can we move ahead? We have actually many people here. We have Suresh is there, Basu is there, Mitesh is there, Navin is there, Tarun is there. Okay, very good. Many people joining, but yeah, I'd like you guys to be more interactive, okay? More and more talkative. Don't just give me silent treatment all the time. Okay. So now we'll go like the static one hazard. Similarly, there's another thing known as static zero hazard. What the static zero hazard mean is, you have the truth table, that is a truth law, you have A and A bar. What should that value be? A and A bar, how much should it be?
0.
Yes, very good. It should be 0. But to implement this, what you do, you have A is the input here. You'll have a AND gate over here like this, right? Then you have a NOT gate like this. This is your A bar and this is your Y, right? And your Y should be equal to 0. But it doesn't happen because of the delay in this. This has a delay, means, let me say, this has a delay. This also has a delay. Okay, so let us just, as I showed for static 1 hazard, I'll just show the simulation for static 0 hazard as well. It's a very simple thing. Close it. Static 1 hazard. Let's see, it's just. Okay, this is the static 0 hazard. So you have an AND gate, you have A, you're forming A bar here, and this is your output Y, which should always be 0. But because of those delays, you will see the output Y is most of the time 0. But for a small duration, there's a sudden glitch. There's something known as a glitch, which is causing it to go 1. which it should not happen, but it is happening because of the non-idealities in your circuit. And so when is it happening? When your A, input A is going from 0 to 1, when it is going from 0 to 1, that time it is happening. Why is it happening? Because when A goes from 0 to 1, A bar doesn't go directly from 1 to 0. This still remains at 1. So if your A is 1 and A bar also is 1, the output of the AND gate, it should also be 1. So that is why you have this momentary glitch you have. You have this glitch. Okay, so this is because of the delays in your circuit. And as I was mentioning that he considered the delay to be the same. That is the AND gate delay and the NOT gate delay is the same. Okay. Let us just try. See, because we have simulation, we can just try. What will happen if you see the NAND gate delay over here is 10 nanosecond. Let me make it 20 nanosecond. And this AND gate delay, let me leave it as 10 nanosecond. Let us see what is the change. What happens? So I'll run it again. Okay, so what you can see is your A bar is still having a much more bigger delay. It is having a much more bigger delay. So what happens is, and your AND gate output comes a little previously. It goes 1 for little earlier and then it goes 0. Okay, because that delay still remains the same. That delay still remains the same. Only your input has been delayed. A bar has been delayed because your NOT gate delay has increased. Okay. All right. So any queries in this? Okay, if there are no queries, then we'll start further. Mm, okay. Hazards are very important. They are talked about. So let us go for the final type of hazard. Okay, so static zero hazard, it happens when you go from 0 to 1. This happens when you go from 0 to 1. And static 1 hazard happens when you go from 1 to 0. This is when your static 1 hazard occurs. Okay, now there's something known as a dynamic hazard. And this occurs when there are three, it is a three-level implementation or more. Okay, it is not just two levels. See, this is a two-level case. This is also not a two-level case. Two-level case is you have two-level case is what? When you have your SOP and POS, that is like your two-level based implementation. But when you have a three-level implementation or more, then you have a dynamic hazard. Dynamic hazard is possible. Okay. So let us see one simulation. And this occurs when you have something like A and A bar plus A, something like this. Or you have A plus A bar and A. In such kind of logical expressions, then you can have this dynamic hazard occurring. Okay. Because you can see you have an and you have an or. Okay. Or and. Further, like that. Okay. So let us see one simple example which sir had only shown. That is dynamic hazard from here. So this is the logic gate. So when, if you go through the if you've gone through the lectures, you would know that this is the example sir has shown for dynamic hazard. And so I'm just simulating it to just give you guys the understanding. So okay, this got it. Which is better. So there are actually multiple stages. Multiple stages are there. My input signal C has gone from 1 to 0. Okay, there is a delay because of NOT gate. This also has gone delayed. This is further delayed. Y3 is further delayed. Y4 is again delayed. And because of these kind of delays, your output goes high, low, and then finally reaches its desired operating point based on the truth table. But in between that, there's this glitch. This glitch, which was not supposed to happen, occurs. And this is not like either zero glitch or one glitch. They're like more number of glitches. Okay, so that is known as a dynamic hazard. Hmm. Okay. All right. So yeah, let us consider the sums. Hmm. Which hazard do you think this would be susceptible to? This circuit. Okay. So question, what is your circuit Y? It is equal to A plus C bar, A plus C bar and B plus C or CD. Okay, so I want you guys to answer. Is this a two-level implementation or three-level implementation?
It is 3 level.
Okay, very good. So it is a three-level implementation, right? So that means there is a possibility of having a dynamic hazard. That is one scenario. Next, if you want a static zero fault, then what is the one you should have? You should have some x and x bar should come. Such a term should come. Is such a term going to come over here? Could such a term occur? X and x bar, where x could be your A, B, or C?
It may occur.
Yes, it may occur because there could be a case where you have C bar and C. So this is static zero fault. Another is the static one fault. For the static one fault, what do we have? We should have something known as a X or X bar. So this when it can occur, let us say, let us expand this, or let us make it very simple. You have, uh, let us say A we put at 0, B we put as 1, okay, D we set it as 1. In such a case, what will the output be? 0 plus C bar and 1 plus C, then C and 1. So this will simplify. What is 0 or C bar equal to? What is 0 or C bar equal to what?
It is C
0,
bar.
C bar, correct. It is C bar. What is 1 or C equal to?
1.
Correct, 1. And what is C and 1 equal to?
C.
Correct. So you have a case where it could be C bar or C. And this is your static 1 fault. Okay. So you all three faults are possible. You can have a dynamic fault, you can have a static 0 fault, you can have a static 1 fault as well. Okay. Okay, let's see this question. So which kind of hazard occurs when with this Boolean expression? What do you think is the hazard that is possible?
We need to put it in KMAP, then only we can find out the things.
Okay, correct. So let us do the K-map. Okay, so we have A, B, and C, D. Okay, like this 0 0 0 1 1 1 1 0 0 1 1 1 1 0 0 1 2 3. Wait, this is not required in this case. 10 11 12 13 14 15. Okay, so first is we have to add B D. We have to see where B is. So first let us start with this case B and D. B and D means where when B is 1 in this case and where D is 1. Just here and here, right? So that's why this is B B. Okay. Next is we'll consider case where we have A prime B prime C. So what is that? That is this A prime B prime, and you have C is 1. C is 1 means this case, this case. So that is this one and this one. Next is we have ACD. ACD is this. So that means A is 1, CD also is 1. So CD is what? C and D is 1. And there you have A is 1, that is this case, this case. So that means this one and this one. Okay, it's this one and this one. Then you have B prime CD. Okay, B prime CD. Let us give it this color. B prime CD prime. Where you have CD prime. So this is your CD prime. And you have B prime. That is you have this 0 and this 0. That's why this is your 1 and this is your 1. Okay. Now we have A prime C prime D. So we have where C prime D. C prime D is this one. C prime D. And you need A prime there. So you need A prime means your 0 and your 0. That way this is 1 and this is also 1. Okay. Now the last of all we have this A prime B C. So you have which is your A prime, sorry, not this one. A prime B and C, where C is 1 in which case? In this case and in this case. Right? Is this what you are guys are getting? Hmm?
Yes.
Okay. So now, how do we minimize this circuit? You have to minimize using, let us say, one is you can minimize like this, right? You can minimize. Okay, let's draw. Sorry, let us draw the red case. Red case is this one. So this is your B and D, right? Then you have A prime, B prime, C, which is your orange, which is this is your case. Orange is this case. Okay. Then you have your blue case, A, C, D. A and C and D is this case. Okay. Then you have your gray case, B prime, C, D prime. B prime, C, D prime is this one. So this is your case. Okay. This is your case. Then you have A prime, C prime, D. This is your green. So this is your A prime, C prime, D. And you have your A prime, B, C, which is your uh, A prime, B, so A prime, B, and C. So this case. Okay. Sorry, that's black. Okay. So which hazard do you think could be possible in such a circuit? At most, it could be a type 1 hazard, but
Yeah, type static one hazard.
static 1 hazard because there are still few things which are not completely connected. That's what I'm thinking. That this case is there, as well as
Yes, yes.
this case also is there. So further, this also is there. But I don't know till what extent we have to go to that we can be sure that the hazard has been removed. That is something also is to be checked. Mm. Okay.
That two part would that two part can only be there, like 11 and 10
Mhm.
and 1 and 3.
Okay,
That
11
two
and
will
10.
be 11 and 10 and 1 and 3.
Okay, okay. They have to be handled, right?
Yeah.
Okay, so you're saying the sorry, it is
No,
not.
and also 2 and 6 also
Yes, yes, yes. That's
maybe.
what I'm saying. So you need to have the 11 and 10, right? Then you need to have the 2 and 6, and you need to also have
And
the
1 and 3.
1 and okay. So 11 and 10, if you want to add, if you want to add 11 and 10, that is actually equal to your A, B bar, and C. And 2 and 6 is actually your A bar, C, D bar. And 1 and 3 actually is your A bar, B bar, D. Okay. So if these things are added, then you can be sure that the static 1 hazard will not occur in this circuit. Okay. Right. So let's proceed further. Now, this we have done. Okay. So this is the question. Let us just take a screenshot. It's very slow. Okay, you have to find the gate input cost without counting NOT gates and gate input cost counting NOT gates. So we have to find the gate input cost. Okay. So for this gate, let us say this A, B prime, C. For A, B prime, C, how many inputs are there to this gate?
Gate input cost means we have to find out what are all the literals available.
Okay.
So by the way, 1, 2, 3,
There are
4,
6
5, 6,
inputs, right?
7, 8, 9, 10, 11, 12, 13.
13. Okay, like let me say like how I looked at it. There's A, B prime, C. There are three inputs. A, B prime, D. That has another three inputs. E, let's ignore. A,
Yes,
C,
like
F
this.
has three inputs, and A, D, F also has three inputs. that all those equivalent goes to another OR gate. So that has 1, 2, 3, 4, 5. That is 5. Okay, so that's why it has gate input cost is 17. Gate input cost is 17. Now we have to know that if you have a NOT gate, you have a NOT gate, it means you need an additional gate, which means an additional input. So you see you have B prime is there. So you need one NOT gate. Now do you see any other C prime, D prime, E prime, A prime, F prime? No. B prime is repeated twice. B prime is repeated here and it's also repeated here. But you need only one input. The output you can send it to both places. So that's why if you have a NOT gate 1, then the gate input cost with NOT gate is just 17 plus 1, that is equal to 18. Okay.
Yes.
Okay. 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 So could you guys introduce yourselves? Like I've been teaching you guys, like one of you could say from whether you're doing BTech, whether you're studying, whether you're a professor, you're doing masters. If you could unmute and in, introduce yourself, it's very good. Also, you could send a text message also. That would also be very good.
Hi, this is Suresh Kumar from.
Okay.
I am working as an assistant professor in Government College of Engineering, Srirangam, Tamil Nadu.
Okay. 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 Nice. 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 Yes. So you teach this subject over there.
I was teach this subject,
Okay.
but this time I didn't because it comes by art semester. So this
Mhm.
is it is now happening even semester.
Okay. 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 All right. All right. Okay. What about Tarun? Okay. So let us start with the very difficult, not difficult, little bit more involved, more elaborate thing. That is the QM algorithm. Okay. It is known as the Wine McCull MC. I don't know the spelling. It is USKY something. Right? QM algorithm. Okay. So let us consider we have a simple circuit that is F A comma B comma C comma D. That is summation of M 4, 5, 7, 9, 13, and 15. Okay, let us make it simple. For this, we have to do the QM algorithm. Okay. So how do you do with such a thing? So what you do is first you write the truth table. There's a bit involved. So let us write it. Or let us do just for the ones. Okay, so we will have A, B. Sorry, go to the next page. We have A, B, C, D. Okay. A, B, C, D, Y, and the integer value. Okay. So this is what 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, triple 0, 1, 0, 0, 1. Then you have 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1 0 1 1 1 1. Okay, so this is a big, large truth table which you guys know. Okay, so we have considered 4, 5. So that is 0, 0, 0. Let me do 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, these are the numbers. So the output is for 4, 5. So we have 4, 5, 7, 9, 7, 9, 13, 15. 13 and 15. Rest all are 0. Okay. So how do we start this? We will group them in terms of how many number of ones they have. Okay, depending on how many number of ones they have, we will group them. So first we will start with stage 1. Okay. Stage 1 where we have A, B, C and D. Okay, we have 4, 5, 7, 9, 13, 15. Okay, let's try to accommodate them. So let's consider case where there is only one. Only one is there. That is happens for 0, 1, 0, 0. Okay, next is that is 4. For 5, there is how many ones? There are 2 ones. So that is 0, 1, 0, 1. That is your 5. Then in which case there's another 2 ones. That is this one also, right? Let me now make it better. So 5 is case where 2 are there. Then 9 is the case where you have 2. 4 is the case where you have 1. Okay, so then 9 means, so you have your 1, 0, 0, 1. This is 9. Then another case where you have 2 ones. No. Next case which you have 3 ones. This is 4 ones. And whereas you have here also, here you have 3 ones. Okay, so 3 ones are 7 and 13. So then you have 0, 1, 1, 1. This is 7. Then you have your 13. 13 it is 1, 1, 0, 1, 13. And the next case where you have all ones are 1, 1, 1, 1, that is 15. Okay, so these are the possibilities you have. So this is your stage 1. Now you have to construct what is known as your stage 2. Stage 2 is what? You have your A, B, C, and D. Okay, I think stage 2. Okay, let us try how much can be done. So you have your first case. Okay, first one, let us see, you have 0, 1, 0, 0. You have 0, 1, 0, 1. So this is same, 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 this is same. Only this is changing, this is 0, this is 1. So what you write? 0, 1, 0 underscore. Okay, it could be either 0 or 1. This is how you write the first thing. And is it possible with the next one? No, because here 1 is, here 0 and 1 is there, then you have 1 and 0. So it is not possible. So now let us consider how it would be when we go compare between the case when you have 2 ones and 3 ones. Which case could match? Which case could match? So now you have between 5, so, and this is actually your 4 and 5. This is 4 comma 5. 4 comma 9 is not possible. Now let us see between 5 comma 7. Between 5 comma 7, is it matching? Yes, because you have 0, 1, 0, sorry, 0, 1, 0, and 1 and wait, 1, sorry, it is 0, 1 and 1. And here you have your underscore. This is what your 5, comma 7. Because only this is changing. Rest all remains the same. Next, you can also have underscore 101. This is between 5 and 13. Okay, between 5 and 13. Now let us see, is it possible between 9 and 7? No. Between 9 and 7, it's not possible because this 0 0 is there. This is 1 1. It is not possible. Let us see between 9 and 13. Is it possible? This is 1. This 0 0 same 1. So it is possible. So between that, it is 1 underscore 0 1. This is between 9 and 13. Okay, this is between 9 and 13. Then stage the next part between the one which has 3 ones and 4 ones. So here how it will be? It will be underscore 1 1 1. This is between 7 and 15. And this will be 1 1 underscore 1. This is between 13 and 15. Okay, so this is what you got your stage 2. So you used 4? Yes, you have used 4. Have you used 5? Yes, you have used 5. Have you used 9? Yes, you have used 9. Have you used 7? Yes. 13 you have used? Yes. 15 you have used? Yes. Okay, so now we have gone from stage 1, we have gone to stage 2. Like we are narrowing down. The objective of QM algorithm is we have to find what are the most essential prime implicants, what are the most essential min terms you need. Okay, so that is why this goes like a recursive algorithm where you go from top to bottom, you check, you compare, you try to find out. So this is the way it proceeds. Okay, it is not, it is a bit complicated, it's a bit complex, but you have to get the flow. Once you get the flow, it becomes easy to understand. Now we have gone from stage 1 to stage 2. Whatever is coming, we have tick mark. Now we have to go to stage 3. Okay, let us go to stage 3. We have A, we have B, we have C, we have D. Now, what can we do now? Which one is matching between 4 and 5? Between this, sorry, between this and this, is there anything common? No, because 0 1 is common, but 0 and underscore cannot match. Underscore and 1 cannot match. So it is not possible. Similarly, underscore and 1 0 1. So underscore and 0 cannot match. 1 and underscore cannot match. Similarly, between here 1 and 0, it's not matching. 1 underscore doesn't match. 0 0 matches. 1 underscore doesn't match. So it's not possible. So 4 and 5 is not getting anything with the next case. Now, let us see between 5 and 7 and 7 and 15. Is anything matching between 5 and 7 and 7 and 15? Is there a match? 0 1 underscore 1? No, there's no match. What about between underscore 1 0 1? Yes, there is a match. So you have your, I'm talking between this and this. You have underscore 1 and then underscore 1. Okay, this is between 5, 13, 7, and 15. Okay, now is there a match between 1 underscore between 0 1 underscore 1? Yes, where underscore is there and underscore is there, there's a match. So you have, again you have your underscore 1 underscore 1. So this is what is this? Your 5 and 7 and 13 and 15. Okay, so this is your stage 3. Okay, that means your output is B and D. So what is gone? 13 and 15 has happened, 7 and 15 has happened, 5 and 13 has happened. So it, now what is left is your 4 and 5 is left, this is left, and this is left. So your output F is BD plus A bar B C bar plus your 5 and 7 is done. Yes, 5 and 7 is done, right? Yeah, 5 and 7 is done. Okay, 5 and 7 also is done. So only 9 and 13 is left. So A plus 9 and 13 corresponds to A C bar D plus A C bar D. Okay. So now we have found out what do you say? These are known as your prime implicants. What is really essentially necessary for you to get this output? Okay. What is essentially necessary for you to get this output? Then we can also like this is the main stuff. Then you can have what is known as essential prime implicants, without which you would not get the output at all. So for that, let us check. So we have to first write the truth table. You have F, and what you have there? 4, 5, 7, 9, 13, 15. You have 4, 5, 7, 9, 13, and 15. So B and D corresponds to which one? B and D means it, is it for 5? Yes, it is for 5. For 4, is it there? No. B and D is for 7? Yes, 7 it is there. For 9, is it B and D there? No. For 13, is B and D there? Yes. Okay. Next, let us do A bar and B and C bar. Is it true for 4? A bar and B and C bar? Yes. It is true for 4. Is it for 5? A bar and B and C bar? Yes, it is true for 5. Yes. Then do we have A bar and B and C bar? No. For 7, it is no. For the also, it is no. Next is A, C bar, D. You have A is 1, C bar and D. So is it true for 9? A, C bar, D? Yes, it is true for 9. Yes. Is A, C bar, D true for 13? A, C bar, D true for 13? Yes. Is it true for 15? No, it is not true for 15. What is true for 15 then? B and D is true for 15. Okay. This is true for 15. Okay. So in this case, all are essentially prime equals. All are essential prime implicants for this case. Because without any of them, you will not get the correct output. But if there was a case, just assume if there was a case where you had this also as an output, this also was there, just assume, then what would be the prime implicants? Then this would be the prime, this would be the then the essential, assume for the case where, assume for this case, then the essential prime implicants, and that would be B and D and A bar, B and C bar. Because in that case, your A, C bar, D, A, C bar, D would not be required. Okay, that is one case. Okay, so any queries in this? Mm, here it's a gate input cost, NAND gate, minimized hazard free. These things have been done. Okay, Let us answer this question too. This question. We have to find a map entered variable MEV map. Okay. So how do we follow compute for this? Okay, we have to use the POS expression. So POS means we group the zeros we group. Okay. So how can we group it? Let me write it A slash BC. Let us draw it big. Okay. 0 1 0 0 0 1 1 1 1 0. This is what D plus E. This is D. This is E prime. This is 1. This is 0. This is E. This is X. Don't care, don't care. Okay. So now this part, these all can be grouped together. And this would be equal to A bar or E. This is one implementation. Next, you could also group this together. So this would be equivalent to B bar, B bar or C bar or E bar. Okay. Then you could group this together. So this would be equal to your B bar or sorry, this would be equal to your B or C bar or D. And if you group this together, it will be equal to your B or C or D or E. Okay. And then you do the dot. Okay. A bar or E. This is your output Y. Okay. Any questions in this? Hmm? Okay, so we have solved these sums. I've also shown certain simulations as well. So what we could do is we can end the session. If you have any doubts and queries, you can let me know. And this session will be uploaded on YouTube also, so you could access from there as well. Okay. So then, thank you for joining. I'll end the session.